makes more sense than using negative numbers. We're going to discuss in a minute then. If we have a car, how do we program the car data type to be either signed or unsigned? Okay, we'll come back to that in a minute. But let's look at some other examples. We also have the int data type, okay, or we use the type declaration int. And now, how many bytes do we use to represent an int in a computer, an integer? And this is this varies from. There is really no standard way. It all depends on the microprocessor we're using. Okay. For instance, the standardized, or let's say the de facto standard right now is that we use 32 bits, okay, to represent an integer. 32 bits is equal to 4 bytes. Okay. Now, there are the new architectures, the 64-bit architecture. Then they might use 64 bits to represent. I mean by architecture, the 64-bit Pentium or AMD chips that you get when you are buy current computers or laptops. They might have 64 bits or 8 bytes to store an integer, which you see is. Then we can store many more binary sequences that with 32 bits. But right now, I think it's still in C. It is well defined as as 32 bits. Now, if you go to something like your thermometer, maybe it's not 32 bits. Maybe your your electronic thermometer. Okay, maybe it's that you don't require a Pentium to actually run an electronic thermometer. So maybe there they use 16 bits or 2 bytes to represent an integer. Okay, so it ultimately it depends on the hardware you're using, how many bytes or bits you use to represent an integer. But this means that basically we're going to have 1, 2, 3, 4 bytes. Okay, so to and we have basically this implies that we have 2 to 32 sequences. Now again, are these sequences signed or unsigned? Okay, and it is easy to see. Let's say we have a signed, that basically we're going to have we will be able to represent numbers from -2 to the 31 to 2 to the 31 minus 1. Okay. Sign. And this is negative. Well, now, how many sequences of 32 bits actually? What's the range of integers that we can represent if we go unsigned? Okay. So let me just. I run out of space here. I'm just going to put it up here. So unsigned. This implies that basically we can represent from integers from 0 to 2 to the 32 minus 1. Okay. So as you can see, it's quite a lot of numbers. Again, this is hardware dependent, but this is in this class we're going to accept. We're working with a 32-bit microcontrollers. Okay. Now we have still a couple of other very important data types. Okay, we have the float. Okay, which again we use basically 4 bytes to represent this. And this implies that if you look at memory, as we discussed before, memory it's like a set of boxes, right? Stacked boxes, one over the other. So that implies that for a float, we're going to be using, and over here is this address 0, over here is address n, okay, of memory. So address 0 and address n. So we're going to be using 4 bytes, okay, in memory. It's consuming 4 bytes to store a data object that is of type float. Okay. And in this case, how do we represent floating? An example of a floating point number is, for instance, 3.1416. Okay. 0.210. 25.0032, etc. Okay. A floating point is characterized by having an integer part and a decimal part. Okay. So how do we represent this? I'm not sure if you covered any of this in digital design, but this is really out of the scope of the class. But this is a very interesting problem in math and computer science, and a lot of people has come up with different ways to represent real numbers. But actually, there is a standard, okay, of an IEEE standard. I hope you all are all familiar with IEEE, okay, at least, otherwise go to the study room in electrical engineering and get some information. But the IEEE takes care of standardizing how we represent floating point numbers, so everybody in the world uses exactly the same representation. Okay, so we're not going to go into the details. Again, it's a more advanced topic. Wikipedia, you check Wikipedia, has a nice discussion which you're welcome to check. But basically, what I want to give you is just the range of values. Okay, so for float, okay, we have the following range of values. We can go from 3.4 times 10 to the minus 38, so a very small number, okay, to 3.4 times 10 to the 38. Okay. Then we also have a double, okay, and so as you can see, this is a very large range, okay. And the most difficult part is how do you do mathematical operations like addition, subtraction, etc. with floating point. That usually microprocessors require a special hardware unit to take care of it. Okay. Now let's look at the other type. Okay. The other type is double. Okay. Let me just put a line here, and that actually uses 8 bytes. Okay. So as you can represent, you have like a much more. Actually, it's like you are doing like a square of 4 bytes, let's say. So you end up with basically the ability to represent from 1.7 times 10 to the minus 308 to 1.7 times 10 to the 308, okay, in terms of values. Okay, again, let me just, I guess, come a little bit closer. Okay, so double is 8 bytes, and those are the values you can represent. Okay. So as you can see, then we have a lot of flexibility in terms of the types of values and numbers that we can store in memory using C language and other languages. Okay. Now that's not the whole story. Okay, we have regarding data types, we have other attributes. We have another series of attributes, and the first one I want to discuss is modifiers. Okay, modifiers give more specific information on the data object. Okay. So these are the modifiers we have, and these are the data types they can modify. Okay, so we have basically we have a short, long, sign, unsigned, const, and volatile. Okay, and to the right I'm